For contact, we have two sets. The first set creates 3 pairs between the bullet, the launcher disc, and the launcher tube. So I'll select them and click on the contact tool. I'll use the default solid bodies option and will pick materials of steel on steel with no friction. And see we're using the default impact properties here. For the second set of contacts, we'll choose the bullet and the pendulum. We don't want any friction, so I'll uncheck that. For the materials, you can experiment, but we find the bullet comes nearly to a stop at impact using steel on nylon. If we picked steel on steel, for example, the collision approaches a perfectly elastic condition, resulting in incomplete momentum transfer. I'll click Calculate so you can see what happens. The bullet does bounce a little, and you can see the spring oscillating since there's no damping on that spring. This screenshot of the contacts dialog provides more details. Depending on the materials chosen up here, the elastic properties can change down here. The default is set to impact, and if you change materials, you'll see the stiffness, exponent, damping, and penetration values changing. Alternatively, you can directly enter a coefficient of restitution by checking that option. Here's the installation image showing the firing spring. It's located between the end of the launcher disc and the bottom of the launcher tube. We used a spring constant of 50 newtons per meter. This entry is the free length of the spring, which you can use to set the potential energy of the spring and thus control the muzzle velocity of the projectile. Here's a review of the dimensions of the spring. The projectile is shown in the firing position. You can mate the components in the firing position and then install the spring in a compressed state. So, this length becomes the length of the spring after it is compressed. When you install the spring in SolidWorks Motion, you enter the free length value in the dialog box. This length is shown here. You can see the spring compression, X, is shown by this graphic. This allows you to calculate the spring potential energy of 1/2 kx squared, where x is the free length minus the compressed length. Here's some sample calculations for setting the projectile launch velocity. You can see the potential energy of the spring is the same as the work done by the spring when we start the simulation. That value is equal to the change in kinetic energy of the projectile and the launcher disk, or 1/2 mv squared. Since we set the launcher disk mass much lower than the projectile mass, you can just use the projectile mass for m. Solving for v shows that you can adjust the spring stiffness k, or you can adjust the spring compression value x to get any value of launch velocity of the projectile that you would like.